Welcome back. In the last section, we mentioned that we can expand the ARIMA model we became so familiar with so it can handle non-stationary data. In this section, we'll go over the intuition behind the model and see how it differs from the ARIMA model. Then, we'll see how well it models non-stationary data like prices before comparing the results with those we got for returns in the previous lectures. We'll see how additional levels of integration affect our model's performance before plugging in stationary data to see how this affects results. Okay, now that we've set our expectations for the future, let's begin by explaining the intuition behind the model and the notation that goes with it. As usual, we'll start with the notation. An ARIMA model has three orders: P, D, and Q. The P and Q represent the AR and MA lags, just like with the ARIMA models. The D order is the integration order. It represents the number of times we need to integrate the time series to ensure stationarity. But more on that in just a bit. Convention dictates that we always enter the three orders in the same way: P first, then D, and finally Q. Of course, that's because P represents the AR components, D the integrated ones, and Q the MA ones. Any model of the sort ARIMA, P0Q, is equivalent to an ARIMA PQ model, since we are not including any degree of changes. Of course, an ARIMA 00Q and an ARIMA P00 would also be the same as an MAQ and an ARP, respectively. Now we're familiar with the notation and how the different types of models are connected, so we can get back to the intuition. When we briefly mentioned the idea behind integrated models toward the end of the last section, we explained them as accounting for the non-seasonal difference between periods to establish stationarity. Hence, even the AR components in the model should be price differences rather than prices. In a sense, we are integrating D many times to construct a new time series and then fitting said series into an ARIMA PQ model. Okay. Now that we know this, let's have a look at the equation of a simple ARIMA model with all orders equal to 1. Since we are going to be discussing differences in prices for the first part of this section, let's suppose capital P is the price variable we're trying to model. Then, the simple ARIMA equation for P would look as follows. Delta P in period T equals some constant C plus phi 1 times delta P in period T minus 1 plus a numeric coefficient theta 1 times epsilon in period T minus 1 plus epsilon in period T. Once again, let's go over all the moving parts of this equation and break it down so we understand it better. For starters, PT and PT minus 1 represent the values in the current period and 1 period ago, respectively. Similarly, epsilon t and epsilon t minus 1 are the error terms for the same two periods. And of course, c is just a baseline constant factor. The two parameters, phi 1 and theta 1, express what parts of the value and error last period are relevant in explaining the current one. Finally, we have the delta p in period t. In math, physics, and science in general, we express the difference between two values as delta. Therefore, the variable delta P in period T is the difference between prices in period T and prices in the preceding period. That means delta P is an entire time series, which represents the disparity between prices of consecutive periods. Essentially, the entire ARIMA model is nothing more than an ARIMA model for a newly generated time series, which is stationary. Of course, this stationarity may require 1, 2, or more integrations. But what will a second integration represent? Well, a second integration will use the time series that consists of the differences in prices and will calculate their differences. Essentially, if we created a new variable Q, which stored the differences in prices, the ARIMA P2Q for P would be the same as an ARIMA P1Q for Q. Okay. We saw that the ARIMA doesn't have any functions like the ACF or PACF, which suggests what the optimal order for the different components is. We can say the same about the ARIMA. After all, it's a more complex model based on ARIMA. So our best bet is to start simple. Examine the ACF of the residual values and get a better feel about which lags to use. It's important to note that we lose one or several observations when we deal with integrated values. Just like with returns, this is unavoidable. The issue comes from the fact that there is no previous period where we wish to integrate the very first day of the dataset. In our case, that's January 7th, 1994. Similarly, if we integrate 2 times, we'd lose 2 observations, one for each integration. Even though we'd have an integrated difference in prices for the second day of the dataset, we wouldn't have one for the first to compare it with. Therefore, we'd have a missing value for the second day of the time series after integrating twice. Simply put, for any integration, we lose a single observation, so we should be aware of this when making our analysis. This is important because, as you may remember, having empty values prevents the imported ACF method from compiling. You'll see what we mean in the next lecture. Now that we've learned how the ARIMA model works, we're ready for some hands-on experience. Thanks for watching. Welcome back. In this lecture, we're going to see how to fit a time series into a simple autoregressive integrated moving average model. Just as before, we use the term simple to express any model with all orders equal to 1. Of course, we'll comment on the coefficients and examine the model's residuals to get an idea of the appropriate orders we need to use. Let's get coding. To conduct analysis using integrated models, we need to import a new package first. If we want to be perfectly correct, we won't import a new package, but rather import a new method from a package we've used before. Using the from import structure, we wish to import the ARIMA method from the Stats Models TSA ARIMA model library. Indeed, we used the same library when we imported the ARIMA method. But loading the entire package seems wasteful when we only plan on using a single method. Okay. Now that this is done, we can move on to fitting the simple ARIMA model. Again, we define a model variable that stores the model specifications before we fit the data. Of course, we can use underscores to clearly separate the different orders of the model to avoid confusion. Next, we set it equal to the ARIMA method, as opposed to the ARIMA we used up till now. We then pass values to the arguments of the method. The only major difference here is that the orders argument takes 3 values, one for each of P, D, and Q, in that precise order. Great! Next, we must fit this model and store the results in an appropriately named variable before we present the summarized outputs on the screen. Once we've run the code, we can examine the summarized table. We can notice that there are only 2 coefficients besides the constant, one for the AR and one for the MA. But why is this so? Doesn't the model have a total order of 3? Well, if we go back to the simple ARIMA equation, we can see that we only need to estimate 2 coefficients, phi1 and theta1. Thus, the integration order has no effect on the number of parameters we need to estimate. Integration means that we are transforming the underlying data, while no modeling is performed. Hence, any ARIMA PDQ model will have as many coefficients as its non-integrated counterpart, the ARIMA PQ. Okay. We can examine the p-value column and see how the 2 coefficients are significantly different from 0. As for the constant term, we notice that it is not significantly different from 0. On the one hand, this is somewhat surprising because that wasn't the case when we were examining prices before. However, that was the case in most, if not all, summary tables we got for returns. Hence, the integrated time series is a lot closer to returns than to prices. After all, integration consists of calculating differences. In fact, if we have a side-by-side comparison with the summarized tables for both returns and prices, we'll clearly see how closely the integrated results resemble price returns. Okay, so next up, we want to have a quick look at the residuals of this model and their ACF. We go through the tried and tested process of extracting the residual attributes from the results variable and feeding them to the plot ACF method. Of course, we also set a title and run the necessary plt show command to visualize the graph without any of the Jupyter-specific texts. The ACF we see is a straight line with no plotted points for any lags. This means the ACF failed to compute for some reason. As mentioned earlier, this is due to the missing value at the first element. Since the ACF starts by trying to compare elements from the very first one going forward, a missing value at the very beginning causes it to break. The easiest solution to this problem is to remove the very first row of the data frame. If you recall, we initially did this when we were dealing with returns. Of course, removing data might affect our analysis of future models, so we need to create a backup data frame if we wish to remove rows. However, a much more efficient workaround is to use the residuals from the second period onward. That way we can ignore as many rows as necessary to plot the graph of the ACF for the residuals from a specific model. However, we won't be losing information for future modeling by removing elements. All right. When we call the plot ACF method, we pass on the new column from the second element onwards. In case you need a hint on how to do this, simply type bracket 1 colon bracket after the name of the variable. This notation says we're using all the elements starting from the one with the index 1. Of course, indexing in programming almost always starts from 0, so 1 represents the second element. Perfect! We can observe that the third and fourth lags are highly significant. Furthermore, our prior experience suggests that incorporating these lags into our model might significantly improve performance. Fantastic! We're now ready to test high-level ARIMA models. Thanks for watching. Welcome back. We already fitted higher lag ARIMA models in the previous section. Therefore, doing so for ARIMA should feel very intuitive. However, since we saw how time-consuming and strenuous the entire process is, we've structured this lecture in a way that will help us avoid doing all the unnecessary trial and error steps. More specifically, we've already fitted many of the relevant ARIMA P1Q models, and we'll draw your attention to the most important ones. Of course, it's good practice to compute those on your own for homework. That said, let's pick up where we left off last time. We saw that the third and fourth lag error terms were highly significant, so our experience dictates we try and see how the models that contain them perform. To save you the time of going through all models, including any number from 1 to 4 AR or MA coefficients, here's a list of the ones that yielded all significant coefficients at the 5% level. Among the additional 15 models, excluding the simple ARIMA model, there were 5 that satisfied the significance criteria. These were the 112, 113, 211, 311, and the 312. Somewhat surprisingly, none of the models which contained 4 AR or 4 MA coefficients yielded all significant coefficients. Given that we've ruled out most of the models, let's focus on the ARIMA 111, and these 5 models to find the best model. Since we've pre-selected them, we already know that the values are significant for all these models. Thus, we don't need to examine their summary tables at the moment. Of course, you can do this on your own after the lecture. We can define and fit these models simultaneously in a single cell. Of course, doing so is entirely up to us, and we can split them into separate cells without affecting the analysis. To save some time, you can define and fit one model and copy the code 4 more times. Afterwards, simply change the names and orders accordingly before executing. As always, make sure to provide enough starting AR lags for each model to allow the execution of the fit method without crashing. If anybody needs a refresher on how to set these initial lags, we simply give a numeric value greater than the AR order, P, to the start AR lags argument when we fit the data. In this case, we only need to set these starting lags for the ARIMA 312. However, remember to account for them with more complicated models. Great. We have all 6 models fitted, and we can print out their log likelihoods and AIC to determine which model is the best fit. Of course, we do so by extracting and printing the LLF and AIC arguments of the results variables associated with each model. For clarity, we should specify which model these values are for. Also, we can repeat our previous steps where we prepare the code for one model and then copy and paste it several times to save up some time typing. Every time you use this approach, make sure you change all the necessary names of the variables you are using and double-check your notation. Okay, here are the results. The comparison of the numbers show that ARIMA 113 yields the highest log likelihood and the lowest AIC. Thus, it immediately becomes the front runner of our shortlist. But that's not all. Since the ARIMA 112 and the simple ARIMA model are both nested for the 113, we need to run the LLR test to make sure it significantly outperforms them. When comparing it to the ARIMA 112, we don't have to specify a value for the DF argument, since the default one is 1. Of course, if you wish to specify it, doing so won't affect the results. As expected, the test returns a value of 0, which indicates that the higher complexity is necessary. So our next step is to run the same test for the simple ARIMA model. However, since the difference in degrees of freedom between the two models is 2, we need to account for that by setting the DF argument to 2. As expected, we get another p-value of 0, so the 113 appears to be the best choice out of the bunch. So far, so good. To avoid analyzing the statistics in vain, let's start by examining the ACF of residuals first. Only if they resemble white noise, we'll proceed with examining and discussing the parameters from the summary table. Otherwise, we'll try to find a better fitting model. Once again, make sure to ignore the first row of the data frame before running the ACF. Now you can either type out the entire code, where we extract the data, plot it and give a title, or simply copy it from the ACF for the ARIMA 111 residuals. As always, when we wish to reuse our own code, we need to make sure to adjust the names of the variables to correspond with the model we're using. Additionally, we need to make the necessary changes to the title as well, since we're no longer using an ARIMA 111. Perfect. In our next lecture, we'll discuss the results and see if anything else needs to be done. Thanks for watching. Welcome back. In our previous lecture, we found that the ARIMA 113 is probably the best fitting model. Then we plotted an ACF based on it. So let's discuss the resulting graph. We see that fewer lags have significant coefficients in comparison to the simple ARIMA residuals. However, the sixth one is still highly significant. Therefore, there might exist a better model, which goes up to 6 lags back. And here we go again. We must check all models up to ARIMA 616 to see if there's a better fit. Since this includes going through 20 distinct models and their coefficients, once again we did this check to help you out. Only 2 models yielded only significant values, the ARIMA 613 and ARIMA 511. If you recall from the last section, the ARIMA 51 was our preferred choice for price returns. Thus, the fact that ARIMA 511 is a good estimator for prices isn't all that surprising. At the end of the day, we're using the same dataset. In addition, the ARIMA 613 contains integrated values for up to 6 periods ago, so it should include the significant coefficients from the ACF graph. Hence, both the ARIMA 613 and the ARIMA 511 seem like solid options for the best possible estimator. Since we want to compare them against one another, now would be a great time to define and fit these two complicated models. Once again, you can copy some of the code we already wrote and make the necessary adjustments to the variable names. Next up, we should extract and showcase the log likelihoods and AICs of these models to determine which is better. Plus, we should also include the ARIMA 113 since it outperformed all the other simpler models. Just like earlier, simply copy the code where we printed the log likelihoods and AICs and then make the appropriate changes. Good job! We clearly see that the ARIMA 613 is the best in both criteria since it yields the highest log likelihood and lowest AIC, so it is probably the best estimator we can use. Since both the 113 and the 511 are nested in the 613, we can use the LLR test to guarantee that the additional complexity is worth it. We can reuse the LLR test code we wrote when comparing the ARIMA 113 with its nested models. By first comparing the 113 and the 613, we need to set the degrees of freedom argument to 5, since the former has 4 and the latter has 9. If we get an error here, you must go back to your LLR test function and set the starting AR lag values to something sufficiently high. That way, we won't have this issue, even with very complicated models. After doing so, the LLR test yields a p-value which is less than 5%. Hence, the higher complexity is rationalized because it earns significantly higher log likelihood. Now let's compare the 613 with its other nested model, the ARIMA 511. Make sure to set the degree of freedom to 3, since the former requires 9 lagged coefficients, whilst the latter contains only 6. Somewhat surprisingly, we get a relatively high p-value of 0.117, which is greater than 0.05. In other words, the higher model fails the LLR test at the 1, 5, and even 10% significance level. This is an indicator that the more complex ARIMA 613 does not yield a significantly higher log likelihood compared to the simpler alternative. Hence, we would opt for the ARIMA 511 as opposed to the ARIMA 613. Now let's have a look at the ACF of the residuals for our model of choice. Of course, you can again copy the code for the ARIMA 113 function and make the necessary adjustments so that we observe the results of the 511. Make sure you ignore the first row to prevent the ACF from terminating early. After we presented the graph, we can see that none of the first 15 residuals have significant coefficients. This is fantastic, since we managed to capture the effects that were incorporated into the 6th lag without directly including it into our model. We still see some significant coefficients many lags into the past, but we know that the further back in time we go, the less relevant the values become. On one hand, if we include up to 35 lags into the model, we will be able to have white noise residuals. On the other hand, it's important to remember that we want this model to be able to predict other time series data as well. Taking 35 lags will result in the model parameters becoming too dependent on the dataset, which will, in turn, take away from its predictive power. Hence, after careful consideration, we decided to stick with the ARIMA 511 as the best estimator for prices. For homework, try printing out the summarized statistics for this model and comment on the coefficients. In the last few lectures, we assumed that the best fitting model would need only a single layer of integration. But what if there existed a better model with more layers? We'll find the answer in the next lecture. Thanks for watching. Welcome back. Last time we only examined models with a single degree of integration, since we assumed it was sufficient. This time, we'll discuss if that is the case and what to do if it isn't. So, without waiting any longer, let's begin. For starters, let's look back to the genesis of this section. We only rely on integration when our time series doesn't come from a stationary process. Hence, if a single layer of integration accomplishes this, any additional ones are unnecessary. Okay, so how do we go about finding out if the integrated dataset is stationary? Well, we can manually create an integrated version of the original time series and use the augmented Dickey-Fuller test. Sounds like a plan. Let's get coding. We'll start off by storing the new dataset in a column of our existing data frame. We'll call it Delta Prices to remind us these are the differences between the index prices from period to period. We'll then use the difference method, .diff, on the market value column of the data frame. We'll pass on an argument value of 1, which will indicate to the method that we are looking for the differences between values 1 period apart. Of course, this will cause the first row of the data frame to have no data available, since it has no prior value. Therefore, we should ignore it if we wish to conduct any model testing. Some of you might doubt if we correctly generated the dataset. One way to test that is to fit an ARIMA model equivalent of an ARIMA one we have fitted for prices. Since we started with the simple ARIMA model and observed its summary table in the beginning, let's use that. In other words, we want to fit an ARIMA 1.1 to the delta prices. Since an ARIMA 1.0.1 is equivalent to an ARIMA 1.1, we'll just use that instead of importing the ARIMA method from the last section. The good news is you already know the drill of copying the code for fitting a model and making the necessary adjustments and print its summary table. If we compare this table to the simple ARIMA results we got earlier, we'll see that they have identical coefficients and p-values, which are what we care about most. After you've made sure this dataset is very close to the integrated version of prices our model fits, it's time to run the augmented Dickey-Fuller test. We simply type sts.adfuller and add our newly created column as an argument. Of course, we must once again ignore the missing values of the first row to make sure the method doesn't return an error. After executing the code, we see a test statistic, which is close to 10 times greater in absolute value than the critical 1% value. Moreover, the p-value is 0.0, so we get our confirmation of stationarity. This is fantastic news because it means we have no need for additional layers of integration. That means fitting ARIMA models with d greater than 1 is not recommended. However, for homework, you can try finding the most appropriate ARIMA P2Q model and comment how it compares to the ARIMA P1Q we chose in the last lecture. Make sure you account for the fact that a second-degree integrated model will have missing values for not only the first but also the second row. Of course, that simply means you need to ignore 2 rows, which you can easily achieve using the bracket 2 colon bracket notation. Talking about stationarity, what happens if we try to fit an integrated model for stationary returns? Well, we'll talk about that in the next lecture. Thanks for watching. Welcome back. Last time we talked about how ARIMA models shouldn't be used on stationary data, e.g. price returns. However, even though we said that ARIMA models shouldn't be used on non-stationary data, we still use them to try and model prices, right? Well, there's a difference between these two cases. While ARIMA models can and will estimate stationary data, they are more computationally expensive than regular ARIMA models. By integrating stationary data, we're only making it more difficult for the model to estimate the coefficients. For starters, it needs to generate every layer of integration one by one, and then try to fit the new data using any of the regular ARIMA models we are familiar with. Another issue we face when dealing with integrated models for returns is that we have a form of data attrition. What does that mean? It means we first lose observations because of the conversion from prices to returns, and then we lose even more data points for each layer of integration. The more unnecessary layers we add, the more our model suffers. Let's explore some of the leading issues. The first one is that, as we said previously, these become more and more computationally expensive. The more layers, the more background work the program has to create before fitting the data. Next off, not only do we have to transform the data several times, but we also have to differentiate the values from zero. And the latter becomes harder, as the values become ever so small. In other words, the margin of something being significant or insignificant becomes really narrow. And this can lead to some models failing to converge even after tens of thousands of iterations. Plus, when the numbers are too small, we may encounter numerical instability. In other words, whenever we have many zeros after the dot, the computer may decide to approximate the number to zero, which will essentially lead to losing the information held in, say, the 60th digit after the dot. Last but not least, the more layers we add, the harder it is to interpret the results. For example, imagine we successfully find an ARIMA P4Q model for returns. Then the coefficients wouldn't be the difference between returns or even some slope of their changes, but rather the slope of the slope of the slope. Even imagining this for a second seems confusing and unintuitive, let alone extracting a useful insight out of such results. Just like in the last lecture, you can practice finding the best ARIMA model for returns. Make sure to ignore the appropriate number of rows from the start of the dataset. If you're having some trouble determining this, just remember that you need to skip one row because we're using the returns and then an additional one for each degree of integration. However, be mindful that in practice, you'll never need to rely on an integrated model to estimate stationary data. Talking about data analysis in the real world, there are often additional factors that affect the price of a market index at a given time period. These can be the inflation rate of the country, the market prices of their indexes, or even the price of gas. In the next lecture, we'll introduce a new concept that takes all of that into account. See you all there. Hello there. Last time we mentioned a model that takes into account more than just past prices or past residuals. These are the so-called max models, with the Rmax being the non-integrated version and the ARIMax its integrated equivalent. Since we're talking about integration throughout this entire section, let's examine what the equation of the ARIMax would look like. Delta P in period t equals some constant c plus beta times x plus phi 1 times delta p in period t minus 1 plus a numeric coefficient theta 1 times epsilon in period t minus 1 plus epsilon in period t. Of course, the equation for the Rmax would be the same, except we would use the actual variable, say p, instead of its delta. Now, the two new additions to the model are x and its coefficient beta. Just like phi, beta is a value which will be fitted based on the model selection and the data. But what about x? Well, x can be any variable we're interested in. As we mentioned, it can be a time-varying measurement like the inflation rate or the price of a different index. It can be a categorical variable separating the different days of the week. It can also be a Boolean value accounting for the special festive periods. Finally, it can stand for a combination of several different external factors. The idea is that it can be any other variable or variables that can affect prices, as long as we have the data available for every period. Such outside factors are known as exogenous variables in our regression. We use these values to predict and explain the ones we're interested in, which happens to be current prices in our case. Conveniently enough, the ARIMA method we've been using is fully capable of handling such additional inputs. When we specify the model characteristics once we've passed the time series of interest and the orders, we also need to specify the exogenous argument called exog. The value we want to pass needs to be an array of some sort, since we wish to have values associated with every time period. For instance, we can use S&P prices as this exogenous variable, since we already have them in our data. Thus, let's fit an ARIMax 111 model. Make sure to name your model variable in a way that distinguishes it from other similar models. We choose to do this by adding x, SPX, at the end, to indicate that the exogenous variable is the S&P. Then we set this equal to the ARIMA method as before. We add the time series and the order as we're used to. Finally, between the two, we set the exoge argument equal to DF SPX, which indicates the S&P prices. If we fit this model and print its summary table, we're going to see that we get an additional row for the S&P prices. Their p-value suggests they aren't significant here, but maybe it's because we haven't included all the indexes. For practice, you can try adding the other index prices as an exogenous variable and see if it improves the log likelihood of the model. To do this, just pass them as an array of exogenous variables when defining the model. However, not all models are used for predicting future prices or returns. Many investors often seek stability when they want to get involved with certain stocks or portfolios. The need to measure volatility has resulted in econometricians developing models to estimate precisely that. But we'll discuss this in more detail in the next lecture. Thanks for watching. Hello again. Before we move on to the volatility models, let's spend a few minutes on something we mentioned in the initial parts of the course: seasonality. Each of the models we examined so far, be it ARMA, ARIMA, or ARIMAX, has a seasonal equivalent. As you can probably suggest, the names for these counterparts will be SARMA, SARIMA, and SARIMAX, respectively, with the S representing the seasonal aspect. In case you need a hint, seasonality occurs when certain patterns aren't consistent, but appear periodically. For instance, check out the weekly YouTube searches for Christmas songs like Jingle Bells. These occur much more frequently over the festive period in December every year. However, the number of times these songs are played is usually a lot lower in June or July. Therefore, a simple AR component won't describe the data well. To elaborate, a simple AR component would severely underestimate the number of times Christmas songs are played in December, based on the stats from November. At the same time, it would also greatly overstate the number in January basing off the values recorded in December, since this genre usually experiences a dip after Christmas. So, what can we do in this case? To account for such a pattern, we'd need to include the values recorded during the previous festive period into the model. In this specific example, that would mean relying on the number of times the songs were played last December. Of course, we can also include the data from 2 Decembers back, or even more. It's a bit like having another series, which is further spread out in time than our original one. Going back to the musical example, the original time series contains values a month apart, while the seasonal one would hold values 12 months apart. Fantastic! Now that we're familiar with the general idea of seasonal models, let's look at the notation we use and what each value means. Compared to the ARIMAX, the SARIMAX requires 4 additional orders. This might sound like a lot, but there's no need to worry. The first 3 of these 4 orders are just seasonal variations of the ARIMA orders. In other words, we have a seasonal autoregressive order denoted by uppercase P, an order of seasonal integration denoted by uppercase D, and a seasonal moving average order signified by uppercase Q. To make differentiation easier, econometricians have agreed to use lowercase letters for their non-seasonal equivalents. The fourth and last order is the length of the cycle. For instance, if we have hourly data and the cycle length is 24, then the seasonal pattern appears once every 24 hours. Another way to think about it is the number of periods needed to pass before the tendency reappears. Of course, if this is set to 1, then every period is its own cycle. So we assume no seasonality, and the pattern is just autocorrelation. If we want to inspect a seasonal trend, we need to make sure to set the appropriate cycle length. The last order is represented with a lowercase s, because it sets the length of each season. Okay, before we show you how to fit a seasonal model in Python, we need to quickly explain how the 4 new orders work in unison. Essentially, the length s expresses how far away the seasonal components will be from the current period. So if we have a model with seasonal orders of 2, 0, 1, and 5, then we're including the lagged values from 5 and 10 periods ago, as well as the error term from 5 periods ago. Since each cycle is 5 periods long, and we're taking 2 lagged seasonal values, we're simply including the values from 5 and 10 periods ago. Similarly, we add the error term from 5 periods ago. To generalize, we're interested in every sth value. We start from the sth and go all the way up to s times p. The equivalent is true for seasonal integrated values and seasonal errors as well. Next up, let's see what the equation of a Sarimax model of order 1, 0, 2, and a seasonal order 2, 0, 1, 5 looks like. The interesting part here is that every seasonal component also comprises additional lagged values. If you want to learn why that is so, please check out the supplementary file accompanying this lecture. So, from the equation, we see that the total number of coefficients we are estimating equals the sum of seasonal and non-seasonal AR and MA orders. In other words, we're looking at a total of P plus Q plus P plus Q, many coefficients. The non-seasonal ones are expressed with lowercase phi and theta, while their seasonal counterparts are expressed with uppercase phi and theta, respectively. Just like with the orders, the capital letters denote the seasonal components, and the lowercase ones, the non-seasonal. Perfect. We've explained the theory, so it's time to start coding. We start by importing the method we'll be using. The relevant module is called Stats, Models, TSA, State Space, Sarimax, and the method itself is titled Sarimax. After running the cell, we're ready to define and fit any Sarimax model. Let's go for a model that has 1, 0, 1 as its non-seasonal order, 2, 0, 1, 5 as its seasonal order, and S&P prices as its exogenous variable. We can start by copying the code we wrote for the ARIMAX model earlier. We should then change the name of the model and results variables to something more appropriate. If we follow our naming system, the variable's name would become extremely long, which makes them prone to error. Therefore, we're just going to change them to Model Sarimax and Results Sarimax, respectively. Take your time to change these wherever necessary in the cell before proceeding. Next up, we need to change the name of the model we're using from ARIMAX to Sarimax. After doing so, we only have to correct the order and set the seasonal order, and we're ready to run the cell. Of course, the former only requires adjusting the values, while the latter needs you to pass a list of 4 values to the seasonal order argument of the method. As we stated earlier, the order is 2, 0, 1, 5. The only thing we have left to do is run the cell and check out the summary table. As expected, we see the exact same coefficients we discussed when examining the model equation. There are several new test statistics and values you can see at the bottom, but no need to worry about them right now. If we've piqued your interest about seasonal models, make sure to check out the supplementary files accompanying this lecture. Additionally, for homework, try to fit several seasonal models for FTSE prices or returns. Feel free to experiment with the order, both seasonal and non-seasonal, as well as with the exogenous variables. You can also try examining a different time series, like Nikkei prices, and comment on the cyclical patterns you find. So after this quick detour, let's get back on track. Next time, we'll be talking about volatility and how we measure it. Thanks for watching.
Welcome back. Last time we concluded the lesson with a discussion of volatility. Well, this time we're going to learn about that in more detail. When making long-term, huge purchases, investors often seek stability. That's why as long as a portfolio rarely experiences big shocks, they're willing to consider it. And here comes the need for special models that measure volatility. For starters, when we talk about volatility, we're talking about the magnitude of the residuals. We don't care if they're positive or negative. We just care how off our predictions are. Hence, a positive shock or a negative one is equally unpleasant since we're seeking stability. That explains why volatility is synonymous with variance and why we want to avoid it. Lower variance signals stability, which in turn suggests lower risk. Thus, measuring volatility is key when we want safety in our investments. But how do we disregard the difference between positive and negative signs in our analysis? By transforming the data. Our approach is simple, yet effective. We square the values. Not only does this solve the positive-negative conundrum, but it also penalizes high differences between true values and predictions more. This properly increases the importance of big, unpredicted shocks and allows us to measure the conditional heteroscedasticity of the data by taking into account past values. These models are called autoregressive conditional heteroscedastic, or ARCH models, and we will spend the next section explaining how to use them. Thanks for watching.